Assalamualaikum warahmatullahi wabarakatuh. We are from Group 5 of PIT 33703 Fuzzy System Development, and today we are going to present about our group project, which is the breast cancer survival risk classification using Fuzzy Inference System. Before we dive deep into the project, let me present to you the group members of this project. Our leader, Muhammad Wafiq bin Amrin, me, Muhammad Firdaus, and lastly, Nur Zarifah binti Sulaiman. To understand the reason for our project title, I will explain the background of this project. Breast cancer is one of the leading causes of mortality among women worldwide. According to WHO, World Health Organization, in 2022 alone, an estimated 2.3 million women have been diagnosed with 670,000 deaths globally. It is not a small amount. This cancer can happen to anyone, not only to women, but to young women, even men. And based on previous data, old-age women are more susceptible to this disease. Breast cancer has been around for a long time, with multiple different treatment plans, with each of different implications. Therefore, improving the prognosis accuracy and survival prediction is important in assisting medical practitioners in making informed treatment decisions and providing patients with realistic expectations regarding their treatment. In this study, we implement the Mamdani type fuzzy inference system that helps in medical prognosis, as human medical reasoning, by contrast, is naturally fuzzy that depends on multiple linguistic approximate descriptions rather than numerical values, which most models fail to have tight grasp.
Assalamualaikum, my name is Nur Zaifah binti Sulaiman. I will be presenting the experimental result. This table shows representative test case evaluate using the MATLAB rule viewer. Patient P1, a 30 years old patient, operated in 1964 with a 0 positive nodes. Received a low risk score of 18, correctly predicted as a class 1. Patient P3, age 65, operated in 1958 with a 30 positive nodes. Received a risk score of 82. Correctly predicted as a class 2. Patient P2 represents a misqualified case, age 52 with a 8 positive nodes. The FIS assigned a moderate risk score of 15, predicting class 2, where the actual outcome was a class 1. Next is showing the classification accuracy. The overall classification accuracy achieved by the FIS on the full 306 patient dataset is 72.2%. The accuracy matrix in table revealed that the system correctly identified 117 of 225 survived patients and correctly classified 52 of 81 patients who died within the 5 years. The positive predictive value for class 1 is 85.4%, and the positive predictive value for class 2 is 48.6%. Lastly, the results show that the classifier performance is consistent with a previous study, achieve accuracy between 65% and 79%. However, the fuzzy inference system provides not only good accuracy, but also a better transparency due to its rule-based approach. The model shows a higher sensitivity than specificity because the dataset is imbalanced, with more patients belonging to the survival class. This causes the system to be slightly biased toward predicting survival. Some misclassification occur due to limited data feature, as important medical factors are not included in the datasets.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Wafiq bin Amrin, and today I will be explaining the breast cancer survival system inference fuzzy. So, on this fuzzy inference system plot page, it shows the overall structure of our Mamdani type 1 fuzzy inference system for predicting breast cancer survival risks. So, this system consists of 3 input variables and 1 output variable. The 3 inputs are age, year of operation, and node of the cancer, while the output is survival risk. For input 1, the first input is age, which is divided into 3 fuzzy sets, which is young, middle age, and old. Triangular membership functions are used to represent these age categories. Next is year of operation, representing the patient's year of operation, which is also divided into 3 fuzzy sets to classify different time periods. And input 3, which is nodes, which represents the number of positive axillary lymph nodes which is detected inside the breast. This variable is categorized into three fuzzy sets corresponding to different levels of node involvement. On the Mamdani inference engine, all three inputs variables are processed by the Mamdani Type 1 fuzzy inference engine. The system evaluates a total of 15 if-then fuzzy rules that models the relationship between the patient, characteristics, and survival risk. Next is the output of the survival risk. The output of the variable is survival risk with a range from 0 to 100. It is divided into three fuzzy categories, which is low risk, medium risk, and high risk. Low risk and high risk are represented using trapezoidal membership functions, while medium risk uses a triangular membership function. After evaluating all fuzzy rules, the system combines the result and performs defuzzification to produce a single survival risk score. In summary, this inference system takes age, year, and node as inputs, processes them through 15 Mamdani fuzzy rules, and generates a survival risk score that can be classified as low, medium, or high risk. Moving on to the rule editor. This page shows the rule editor of our Mamdani Type 1 fuzzy inference system. The rule base consists of 15 fuzzy if-then rules that define the relationship between the input variables and the output variable, which is survival risk. The rules were developed based on logical relationships between the patient age, year of operation, and the number of positive lymph nodes. Each rule follows an if-then structure. The if part contains one or more conditions on the input variables, while the then part specifies the corresponding survival risk categories. For example, on Rule 1, Rule 1 states that if the number of nodes is low, then the survival risk is low. Rule 2 states that if the number of nodes is moderate, then the survival risk is medium. Rule 3 states that if the number of nodes is high, then the survival risk is high. The system also uses combination of multiple input variables to improve prediction accuracy. For example, Rule 4 states that if age is young and nodes are low, then survival risk is low. Rule 10 states that if age is young and nodes are high, then survival risk is high. And lastly, Rule 15 combines all three inputs. It states that if age is old, year is early, and nodes are high, then the survival risk is high. A total of 15 rules were created to represent different combinations of patient characteristics and their effect on survival risk. These rules allow the fuzzy inference system to model complex relationships that cannot be represented by a single mathematical equation. So this is the rule inference page where I will move the slider of the age. Let's say if I move it to the 50.5 and the year of operation, maybe 1964. The nodes of the cancer is very large, maybe 50, and the survival risk is 82.3. And if the age is very old and the year of operation is 58 and the nodes are high and the nodes are here, the survival risk is very low, which is at 61.4. Moving on to the control surface. So this surface is generated by evaluating the fuzzy rules for different combinations of age and nodes. As these input values change, the fuzzy inference engine calculates the corresponding survival risk. So the graph indicates that the survival risk generally increases. The number of positive lymph nodes increases. Certain combinations of age and nodes produce a higher risk value, while lower node involvement generally corresponds to a lower survival risk. So in this graph, the x-axis represents the patient's age, the y-axis represents the number of positive lymph nodes, and the z-axis represents the predicted survival risk generated by the fuzzy inference system. The transition between regions are gradual because fuzzy logic allows partial membership instead of strict boundaries. So that is all for our group and the MATLAB demonstration.
In conclusion, as per results and demonstrations that have been presented by my teammates, the model achieved an accuracy of 72.2%, according to a dataset of 306 patient records. Our findings find that number of positive axillary nodes is the most influential factor in survival risk, where patients with more than 12 nodes are more likely to be classified as high risk. Our findings also find older patients, especially with moderate number of positive nodes, tend to have a higher risk levels. After the result and demonstration of our fuzzy inference system, we can see the fuzzy inference system provides an interpretable and explainable approach for medical decision support in survival risk prediction for breast cancer.